Recorded is rolling. It is Tuesday, October 15th. I hope you guys enjoyed your hurricane week off. So last time I saw you guys, we were doing this turntable lab. Still got the turntables out. You guys got the lab page in front of you. So we're going to finish this today. I have some posters and demos, some for review, some are a little bit new. And then want to work towards this centripetal force lab, which is actually on the back side of this lab page. If you just look on the back side of this page. So when we're finished with this lab today, just hold on to it because on the back side is a different lab. We're going to start on tomorrow. All right, so I'll tell you guys towards the end of today a little bit about that so you guys know what to look for. Walking in tomorrow. All right, so other stuff coming up. PSAT is going to be on Thursday, which is in 2 days, because today, of course, is Tuesday, then there's Wednesday, and then Thursday. Now, some of you guys are taking the PSAT. If you have a question about that, let me know. I have an Excel file I can check. But guys, most of you guys are going to relocate to where? Media Center. Are you going to come to this room? No, Media Center. And that'll be on Thursday. I'll be with you guys in the Media Center and got an activity there. Right. Another one that's coming up. So 1 week from now, Tuesday, is the ASVAB. I think making all 11th graders take it, I think. And I think this room is being used. Okay, so that will affect our schedule, but I don't have a bunch of details on that. I don't know who's testing where or what I'm supposed to be doing or anything like that yet. Right, so all I know is that something's going on. It's going to affect us. Okay. All right, quiz information. Let's show you guys here. This is for the entire rest of the semester. You guys ready to see an outline for the rest of the semester? Because it's a little bit weird, but there's some reasons why things ended up this way. So we're just going to write that, and I'll show you guys exactly what's going on. So Q1 grading period would normally be finished by now, but it's been extended for a few more days because of the hurricane, whatnot. So yeah, double check this class, your other classes, make sure you got all your work in. And if you're missing anything, then bring it in. You guys got a couple more days. Okay. So we're just starting on the circular motion. We were doing the kinematic version of this with the turntable. I need to show you guys gravitation, show you guys orbits. And then a couple of weeks from now, I'll get you guys to your next quiz. It'll be a take-home quiz. That'll be all good. Okay. The next topic we're going to be talking about a couple weeks from now is going to be energy. Again, that's going to come with a take-home quiz. All right, so now we're looking at about a month out from now. Right. All right. Then guys, heads up. So you guys got a good month warning to know this is coming up. I'm going to get you guys an in-class quiz. This is going to be comprehensive. So this will be pretty much anything up to that point. And so go back, look at projectiles, look at Newton's laws and forces, right? All that's going to be on this comprehensive quiz approximately a month from now. Okay. Right. Then I'll teach you guys momentum and collisions, give you guys another take-home quiz. Right. Then there's going to be another comprehensive quiz. This is going to be focused just on energy and momentum for the most part. So those two topics. Right. Right. Then we'll be getting pretty close to the end of the semester. Now, normally I fit in rotational dynamics in December, right before the midterm. I don't know if I'm going to be able to this semester. It's just been such a weird semester with so many weird things going on, like hurricanes and whatnot. So I might bump this to January, this like torque and angular momentum and that kind of stuff. So that might be January, which if it is, that'd be okay anyway. Most physics classes just pace out that way naturally anyway, right? Right. But anyway, one way or another, that'll get us to the midterm. Right, so you guys good with agenda? Everything going on? What's going on? All right, are we good? All right, let's do some top scientists here. So here's my top scientists for my honors classes. This is for the forces quiz that was due a couple days before the hurricane. Right? Right, so got that. So awesome job if you're on that list for top scientists. Hey, I'm probably going to use this video for all my classes. We're all finishing the turntable lab today. So in case I do, here's for my AP students. They have a different type quiz. Right, there's some AP students. Right, and then here's my conceptual students, top scientists. All right, so awesome job if you are a top scientist for the forces dynamics quiz. All right, so turntable. All right, you guys have on, okay, so there's the lab page. You guys all got that lab page in front of you. Okay, there's this turntable also in front of you. Right, you guys have probably one mass slug you put somewhere near the edge. Right, I'm using these 3 Roosevelts, and I'm really just focused on the outside Roosevelt, but I have the other ones there just for context so you can kind of compare their motions. Okay? So if I focus on this guy right here, you guys remember I had you guys do a 2-part story. I know this goes back over a week ago, so I'm going to do a little bit of recap right here. Remind you guys some things that we've only spent a day or two really talking about. Okay? So I had you guys do 1, 2, 3 full rotations, and then take your hand off and let it naturally slow to a stop. You guys remember that? Right? Right. Now, while you were rotating at 3 full rotations, you guys timed how much time that took. And then slowing to a stop, you guys measured with a protractor what was that angle slowing to a stop. We converted that into radians and then recorded all that information. Did a couple calculations, and then that's about where the bell was ringing, right? Also, since there's some new concepts, we do a fast recap on some new stuff you guys are seeing. So far, we're just focused on this kinematic stuff here. I'm going to flip this off. Here we go, flip this off. All right, because yeah, it's getting a little bit scratchy here, but all right. So, how far is something turned? How fast is it turning? And if it's speeding up or slowing down, I'll call that angular acceleration. So theta, omega, alpha for angular displacement, angular velocity, angular accelerations. Like that, right? Right. Oh, so that's all we're focused on so far. Tomorrow, we're going to get started on centripetal force, what force is actually holding something on a curved path. And then these bottom rows, don't worry about for a few months. Okay, so the recap there. Right. We got, this right here. Hey, this looks like your turntable. Maybe this could be like my outside Roosevelt right here, maybe right here. Right. So here's how far it's turned. Here's how fast it's turning. And if it's speeding up or slowing down, its rotation rate. I could call that angular acceleration with alpha right there. Right. Then there were tangential linear equivalents, right? Like, for example, if this was a giant circular racetrack, how far have you gone around? As maybe a circumference could be an example of that. Maybe like this x, right? Or how about this? How fast? So what if you have either a speed gate and this is zooming through a speed gate, or if you're in a car, you look at the speedometer on your car as you're driving around a circle, right? Like how fast is it saying going? That's a linear concept. I'll call it a tangential velocity, right? So how does that have to do with how fast the turntable's turning? Right? Or in case of like how far have you gone? How fast do the turntables turn? Okay? Guys, to go from angular information, theta, omega, alpha, to linear information, x, v, a, all you have to do is multiply by what? Radius. From your radial distance from the center. You see that? Right? And we did do that too. So that's the show. Right? So you guys remember we were recording this angular information here, right? Like how far is it turned and radian, right? And then say how far did it move, and say centimeters. Yeah, just multiply by the distance from the center. Right? Right. So speaking of this angle theta, you guys see this angular displacement theta, right? How far is this turn? I can think of at least 3 different ways to measure how far is the turntable turned. Okay, so what's one way you can measure how far it's turned? Huh? Did you say degrees? Yeah, totally. And that's what's on the protractor, degrees. Yep, that's a good way to do it. What's another way to do it? Radians. Right. And the third way could be complete revolutions or rotations, right? But guys, out of those 3 ways, degrees, revolutions, and radians, what's the only one of those as a unit that you can plug into this theta to make this equation work? What's the only one? Radians. Has to be in radians. Can you put degrees here? Can you put revolutions here? Has to be radians. Right? By the way, 1 radian is about how many degrees? About 57 degrees, about, right? And how about this? 1 revolution or 1 rotation is 360 degrees, right? Right. How many radians is that? How many radians in 1 full circle? 2 pi, right? As in circumference equals 2 pi r, which actually follows from that too, right? Actually, that's a specific version of this. Circumference equals 2 pi r if you make exactly 1 round trip, right? You remember that? All right. There's also these kinematic formulas. We did use these a little bit to calculate the stopping time. Last week we did that, right? So that looks a lot like, here, I've got the linear versions right here. Here's the linear versions. Right? Here's the angular versions for a turntable. Who remembers how many different variables are on this entire page? How many different unique variables? 5. Right. Here's how far it's turned in radians. Here's how fast it's rotating in radians per second. And if it's changing, then you have a beginning and ending value. Here's how much time has passed in seconds. And here's maybe the rate is either speeding up or slowing down in radians per second squared, right? And you need to identify how many before you can solve anything. 3, yeah. So if you can identify any 3 of these, you could solve for the other 2. Okay, so that's how it's working. It's got those. All right. So that's all recap right there. I got some more posters I'm going to say for after the lab. Okay, so for now, Okay. We are on this lab page, and I think, yeah, we'd actually gathered all the data by this point. We were about ready to make the graphs. So, reminder how this worked. You guys did 3 full rotations. Guys, every rotation is 2 pi radians. So if you have 3 full revolutions, how many radians is that? What's 3 times 2 pi? So 6 pi. That's where that's coming from. So 3 revolutions, 6 pi radians. You guys timed how much time that was. Now that was holding your hand on, holding it at a constant angular velocity. That many radians in that many seconds gives you that many radians per second. Okay. Okay. And then for the linear tangential values, like how far did it go around? Like if you wrapped a string around and then pulled the string out, right? Guys, how did I get this number, 264 centimeters? How did I get that? Where'd that come from? Who remembers? I think it's just this right here. Isn't it just this right here? Right? Here's how far in, well, meters or centimeters. Here's how far it turned in radians. Here's the radial distance from the center. Well, let me check my math right here. All right, and you guys can check yours too, because you guys probably have slightly different numbers than I do. But I'm going to take the 6 pi radians. I'm going to multiply by 14 centimeters out. My outside Roosevelt was that far out. What is that? Hey, that's my 264 centimeters right there. That's where that's coming from. Okay. And okay, same thing for the singular velocity. At 3.39 times 14, I bet it'll give me 47. So that'd be centimeters per second. Like a tangential speed. If I point a radar gun at it, you'd also think of it that way. Okay. And then the second half of the story, so you let your hand go and it naturally slows to a stop. You measure with the protractor, how far was that? We did a little unit conversion here, got that number in radians. Right? So that was the stopping displacement. Right? I had you guys calculate how much time that was. Now, for context, my earlier classes I had on time this with the stopwatch, but I realized it's actually better to calculate it. So we went ahead and did that with those 3 kinematic formulas. Look back a week ago if you want to see how we did that. Right? Went to, of course, rest, went to stop. We also calculated the rate that it was slowing down in radians per second squared. Right? Multiply these angular values by the radial size, you get the tangential linear values. All right, graph time. So I have 2 sets of graphs. I have the angular set and the tangential linear set. Okay. So these graphs should look familiar, but what the titles and the axes. So you guys see x versus t? Let's go ahead and label this x. It's going to be in centimeters today as a function of t, time, and seconds. Okay, so you guys label that variable unit. So when I go popping numbers on these axes, now the units are already embedded in the axes, the units. So if I wrote something like 5.56 seconds to get to T naught. You guys know T naught is where I take my hand off. Right? So everything before that is constant angular velocity. T naught is when I take my hand off and then keeps moving after that, but it slows to a stop. So that's where I'm getting the 5.56 on. Right, that makes second. Right? Now that 5.56 has the unit seconds embedded in it. Right? Okay, so that's x versus t. I got a v versus t. Let's do velocity and centimeters per second as a function of time and seconds. And then a versus t, that's acceleration. That's a linear tangential acceleration. Okay? And centimeters per second squared as a function of time and seconds. Right? This one's kind of like if you were on a giant circular racetrack and you're tapping the brake and slowing the car to a stop. That's what this graph is going to represent. Maybe the rate the car's slowing down when it slows down. Okay? Okay. Now, those are linear graphs that you guys have seen probably dozens of those at this point in the class. You guys have seen so many. X versus T, V versus T, A versus T. Right? So many stories you guys have seen paired to that. We're going to pair this story too, right? But now this is a turntable. So now I also have the rotational graphs, like the angular versions. So theta versus T. Theta, angular displacement, is going to be in what unit? What unit right here? Radians as a function of time and seconds. We got omega, which is angular velocity. This could be in radians per second as a function of time and seconds. We got alpha is angular acceleration. It could be in radians per second squared as a function, again, of time and seconds. All right. And so now I've labeled all my axes. Okay. So the linear version was x versus t, v versus t, a versus t. The rotational equivalent is theta versus t, omega versus t, alpha versus t. Okay. Radians is how far does it turn? So we got radians, radians per second squared. Boom, 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 boom. All right, you guys good? Again, I did throw 1 time on the time axis. I put t naught. That's the time that you take your hand off. So everything leading up to that is a constant angular velocity. Everything after that is a slow into a stop. Okay, so also, since we've done a bunch of these in class, you guys know I usually start with the middle graph, the v versus t, and then branch out from there. So the first graph, have you guys draw? I'm going to zoom in on it. If you're in class, I just zoomed in. On this omega versus t. You guys see omega versus t. So it's angular velocity as a function of time. You guys have a pencil with an eraser? All right, go ahead. Draw that graph. All right, so we're going to walk around the classroom, see who's going to get this correct. Can you correctly draw omega versus t? So angular velocity versus time. Remember, there's 2 halves of the story. The first half is constant angular velocity. And then at t naught, you take your hand off and let it slow to a stop. What does that look like? Oh, yeah. Right. That's data. All right. You guys are up to a good start. There. Okay, so I'm thinking about in terms of velocity, in this case, angular velocity, something to do with how fast is it spinning, right? How fast is it spinning, right? This is going to be analogous to, and actually the graph right beside it, the v versus t, it's going to look like this also. Is what if you're in a car on the highway going a constant linear velocity? The graph you're making right now, isn't it whatever your speedometer needle is just pointing at? Like how fast you're going, right? How fast you're going. Okay, here, let me put this together with you guys. So, you guys know everything up to t naught is a constant angular velocity. So, I got it spinning. Maybe, say, right after time 0 or something, right? It was maybe like spinning this fast. Then, 1 second later, now it's spinning, hey, it's the same speed. Then 1 second later, hey, it's going the same speed. Then 1 second later, hey, it's going the same speed. Then 1 second later. Right. Do you guys see it's like always the same speed? All I'm doing is just graphing. It's angular speed, angular velocity. Right? And for the constant angular velocity part, it's just a flat line because that's what a constant angular velocity is. That's all it is for the entire Earth spinning on its axis. Doesn't the Earth rotate once every 24 hours? So if you did 1 revolution every 24 hours, it's just always the same. It's a flat line. Now, right at this point, now you take your hand off, it's going to slow to a stop. Okay, slow to a stop. What is final angular velocity equal to? 0. So here's the point 0 down here on this axis, right? So 0, 0. Okay, so I know after some more time, maybe like over here, it's going to slow to a stop. We just stop right there. Right? So in this class, is it okay to assume uniform motion, like uniform acceleration? Which means how does this connect to this if it's uniform? Yeah, constant. So that means you can take a ruler and you just go zip, just straight line. That's it. That's that graph. That's all I'm looking for right there. Okay. Oh yeah. All right. Does that make sense why that graph looks like that? Okay. All right. Let's do the one right beside it. You guys see v versus t? So this is tangential velocity versus time. This is, get a demonstration here. Zoom out a bit. You guys can see this. Okay. This is, if I have this outside Roosevelt, if I have a speed gate right here, and this goes zoom through the speed gate. Or if I have a cop pulls out a radar gun and points it, zoom, like how fast is it going, right? Or if you think if this is a car on a giant circular racetrack going around, zoom, you look at the speedometer on a car, right? I just gave you guys 3 stories that are all the same thing, right? I'm talking about a linear tangential speed. Okay, that's this graph we're going to make right here. Go ahead, draw that graph. I'm going to point my pen to it. Draw that graph right there, v versus t. The tangential speed as a function of time. I'm going to walk around the room again. I wonder who's going to get that graph. Tangential speed as a function of time. Who's gonna figure this out? Right, at least figured it out. Who else gotta figure this out? All right, I think Alexander Payton got this figured out. All right, yeah. Ooh, getting there, getting there. Trip here. All right. All right, yeah. Ian got it figured out. Still got it figured out. All right. Yeah, all right. I think you guys are getting this. You guys are getting this. All right. So I think what some of you guys figured out was, yeah, if you go back to this right here, guys, here's the relationship between how fast is it spinning and how fast is it moving tangentially. All you have to do is multiply by r. But you know what? If this r is constant, so like for me, it was a constant 14 centimeters. If I just, whatever shape this graph makes, if I just scale it by a constant value, it's going to make the same type shape. That's all it's going to be. Okay. So, yeah, that's going to look, right, it starts out a flat line, and then it goes down to 0, something like that. Okay. If I attach a number to it, actually I got some numbers right here. I could if I wanted to. So this could be 3.39 radians per second. And this could be 47.5 centimeters per second. Like that, right? Guys, are these two the same basic shape? Yeah, right. In fact, all you could do, you could take this one, you could just, no, it's a different vertical axis with different units and a different concept. But you could warp it vertically and it could overlay exactly on this graph. Good. Right. Do you think it's going to be the same story with these other graphs? Let's think about this, right? All right, so next ones, let's do these acceleration graphs. So how about angular acceleration? The rate that it's speeding up or slowing down at some point. Right? Go ahead. Point my pen to this one right here. So alpha versus t. Go to make the angular acceleration as a function of time graph. What's that going to look like? Give you guys a hint. Can you derive acceleration from velocity? Because what property of a velocity versus time graph tells you acceleration? It's a coordinate, an area, or a slope. Like a slope, right? Hey, maybe you can take a bunch of slope information from the graph you already have, the velocity versus time graph. Maybe you can figure out the acceleration versus time graph. Just graph all the slopes, right? What's that gonna look like? I don't know if I've seen anybody get it exactly right yet. One more time here. All right. Here, let's do a little review of it right here. Okay. So you guys remember how a velocity versus time graph is really information rich, right? Because it could have all this data in a velocity versus time graph. They throw in some units. Let's call this meters per second. Let's call this seconds. Hey, maybe you have a car break into a stop. Let's just focus. All right, so I'm just going to do a generic example. Right, so I'll call this a car breaks to a stop. Right, we're going back to linear. We're doing this review from a few weeks ago, a few months ago. Okay, so you guys said the slope of this graph tells you acceleration, right? Right. And if you didn't know that, or if you forgot that, or maybe it's gonna be like 5 years from now, and hey, what if you see some graph you've never seen before in your life? You're trying to get as much information from that graph as you can. Like, huh, I wonder what properties of that graph represent what physical variables. Right? Well, look at the units. Because if we're talking about rise over run, suppose somebody's walking downhill. Like, how steep is this hill? So it's kind of a steep hill. How steep? Can I quantify that? Rise over run. Well, the rise, or in this case, the fall, could be in meters per second. And if I divide that by some seconds, rise over run, hey, is that like meters per second squared, which describes an acceleration? Is that true? Right? Okay, so since that unit describes an acceleration, that's how I know the slope is the acceleration. Okay? So more of that graph, but come back to it later. Okay. So, what is the slope of any flat graph? Any constant graph? 0. So everything between time 0 and t naught is 0. In this case, angular acceleration. That turntable was not speeding up or slowing down spinning at all. It was just, hey, that's constant angular velocity, 0 angular acceleration. True? Makes sense? Okay. Okay. Then you take your hand off and it starts slowing down. Okay, it slows down until it stops, and we're assuming at a constant rate. Okay, it slows down at a constant rate. I see a constant slope. Is that called a constant angular acceleration? If you graph a constant angular acceleration, what does that look like on a graph? And is that a positive or a negative slope? So negative slope, and it's constant, negative, constant, put it together, boink. There you go. There's the answer. There's the answer right there. Right. I'm going to leave it that way. One reason is if you were taking an AP class, if that was a multiple choice on answer on an AP exam, they would leave it exactly like that. Right. There are different variations on this. If you got this data from from an accelerometer or something, it might connect those with a really steep line. So if you connect them, that's okay. That's almost vertical, but maybe not exactly vertical. In a math class, they might want to do a jump and maybe like open up one end with like a hole or something. Okay, I'm just gonna leave it like that. Right. Guys, good there? Right. Right. Are you guys ready for the tangential linear acceleration? Okay. Now this one that we're about to do right here, this could be kind of like, here, I'll tell you a story. This could be you're driving around a big old circular racetrack and you tap the brake and the car goes to a stop. Actually, sorry, that's the second half. The first half is constant speed, right? The second half is then you tap the brake and come to a stop, right? Do you guys think this graph is going to look like this graph? Again, the reason that's true is right on this poster. It's just if you know your angular acceleration, and you very simply multiply by radius, it'll tell you the tangential linear acceleration. Okay? So since your radius is constant, any crazy curve times a constant is going to be the same shape curve. It's just going to be stretched by some factor. In this case, 14 centimeters on my paper. So I think this is going to look like, see, flat line followed by a negative flat line, point, just like that. Yeah, there's 4 of those 6 graphs right there. All right, you guys got those? You guys got those? All right, everybody doing good. Doing good. All right. So the kind of tricky ones that I usually say for last, in this case too, is the displacement versus time, or I might actually call this, when we get to the x versus t, distance versus time. So theta could be angular displacement, and x could be, I'm going to call it distance rather than displacement. And I'll tell you guys why. So this is kind of a technical thing, but suppose you're on a big old circular racetrack. Are you guys ready for a tricky question? I think I've asked you guys this before, but I'm not 100% sure. Right? You're on a big old circular racetrack. You start at the start-finish line, and you run all the way around the racetrack, and you stop exactly where you started. Guys, if you stop exactly where you started, what is your displacement always equal to? 0, 0. That's kind of a textbook definition thing, right? And if your displacement is 0, what is your average velocity always equal to? 0, right? So yeah, maybe you'll see that in college. They might ask a question like that. I probably won't, but you might see that, right? So I'm going to switch my terminology to distance and speed, okay? In this case, distance. Okay, just for that reason. So it's more like the odometer of a car. So if you drive all the way around, the odometer just adds everything up. That's called distance. All right. Okay. So that aside, what are these graphs going to look like? Let's start with theta versus t. So angular displacement as a function of time. Go ahead and draw that graph right there. Walk around the room, see what your guys' graphs look like. What does it look like? Who's gonna get theta versus t? And same story, two parts. Oh, I think Elise got them. Right, Elise got them. Everybody else. Okay. The first half of the story is a constant angular speed. Second half of the story is you're slowing to a stop. Now you're still moving forward. Because the whole time, the turntable only turned one way, didn't it? Did the turntable ever turn backwards? It never went into reverse. It was always going forward. Ooh, pretty close, pretty close. Here, I'll walk you guys through this. Let's do another review type question. Okay. So you guys remember a few minutes ago, I was looking at say like a car braking to stop, velocity versus time, something like that. Okay. Let's do a more expanded version of that. So we're going back to the car again. So this is another linear motion type example. Wait a minute. What do I want to do here? Start over. Oh, I want to do two graphs. Scratch that. Two graphs here. Try and make this kind of big for the camera also. For you guys in front of me. Do a couple of big old graphs here. Let's do distance as a function of time and velocity as a function of time. Okay. If you want some units, you can have some units. Maybe this could be meters per second and seconds. Maybe this could be meters. And this could be seconds. That's our convention for this class metric. Okay. But if it helps, guys, could you do miles per hour and hours? And could this just be distance in miles? Right. If you want to switch and think in terms of like miles per hour and hours, you can do that too. Right, same idea. And, throw some times on the board. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So I'm gonna have a velocity versus time curve that looks like this, right? Which pretty well matches your velocity versus time curve. Don't your velocity versus time curves look like that? Right? Constant velocity for a while, and then slows to a stop at a uniform rate. Boom, boom. Okay, so you got that. Okay. Okay. Let's throw some numbers on the board just to maybe this will possibly help. Let's do 50. This could be 50 meters per second. Let's say for 1 second. This is not exactly the turntable, but just get the idea across. Okay. Guys, you go 50 meters per second for 1 second. How far have you moved distance-wise? 50 meters. Right? What if I change the units out? What if you're driving on the what if you're driving on a highway? You're going 50 miles an hour, and you do that for 1 hour. How far have you driven? 50 miles. Okay. So say after 1 unit at a time, let's go back to metric, maybe 1 second, pick it up like 50 meters, something like that. So like that. So point, got a point on the board. If I started at 0, 0, I could, after here, I'll go back to metric. After 1 second, I've gone 50 meters. Okay. But how about 2 seconds? How about this? Okay. Now look at guys, what property of the graph of the V versus T graph tells you how far? It's not the slope, it's not the coordinate, it's an area. Guys, what if I hatch in this rectangle? See, I'm hatching in this rectangle right here. Hatch. Right? In general, couldn't the area of a shape in general be base times height? And for a rectangle, that's exactly true, base times height. If it's a triangle, it's half of that. Other shapes are some other variation. Okay? But it has something to do with multiplying the axes together. Because that's also true of the units. You guys remember a few minutes ago? I was telling you guys, well, if you divide these units, in this case meters per second divided by a second, give you meter per second squared, that tells you something about what does the physical property of the slope represent if you divide them. Okay? Now we're thinking more in terms of area. Okay? So area has something to do with multiplying these units. Because what if I do meters per second and I multiply it by seconds? What unit does that give me? Meters. right? Or my other example, let's do this in American. What if I was in miles per hour and multiply by some number of hours? Going 50 miles an hour. I do it for so many hours. What unit does that give me? How many miles have I gone? Right? So some distance. You see it? Right? So back to here then. Right? Oh, let's throw another unit of time on board. How about one more? Okay, let's go back to meters per second and seconds. So now I drive it, go for another second. Guys, what's the area of this rectangle equal to that I'm hashing in right here? Base of 1, height of 50. Is that another 50 units? Okay. In metric, that would be another 50 meters. So add that to the first 50. Now I'm up to 100 meters total after 2 seconds. 3, 4, 5, 6 seconds. 3, 4, 5, 6 seconds, maybe something like that. Okay. Okay, let's throw another second in the mix. So now I'm going another second. How much further have I driven now? Is that another 50 meters right there? Right. Here's 50 meters. Here's 50 meters. Here's 50 meters. Right. So now throw another 50 meters on the board. Now I'm up to like 150 meters up. Right. Hey, look at that. Now my distance versus time graph is coming together, at least for the first half of the story. Guys, if you're out on the highway and you're driving at constant velocity for some amount of time, you are accumulating distance at a constant rate. And that's exactly what that graph shows. Right? That's it. Of course, both these graphs are telling the same story, just different perspectives. Right. Now the cars break into a stop. Now you guys have seen this before, car break into a stop. It's an old poster. Right? But I want to do a review here, do a recap of why, or let's do this whole thing from scratch. This is good notes anyway. Right? Because now there's a changing velocity. This is kind of tricky. Can I kind of do this rectangle trick? Kind of, except if I split this up into intervals, I got 3 intervals here. That's not exactly a rectangle. That's a what shape? Trapezoid. Okay, and then I have a shorter trapezoid and a little tiny triangle down there. Okay, All right. Although this trapezoid looks kind of a rectangle. It's almost a rectangle. Is that true? Hey, maybe well, especially if it was really tall or really skinny, that'd be closer to a rectangle. What if I do this? What if I take some scissors out? It's scissor time. I'm gonna cut off this this little triangle right here. I'm gonna paste it right over here. Hey, now it is a rectangle. You see this rectangle right here? Right? Look, I just cut out this triangle and I just pasted it right down here. That's true. All right, I could do that with this one. I got like a flat a shorter rectangle. I can do that with this one. Hey, I got another rectangle. You guys see how each of these rectangles has an area that's equal to that corresponding trapezoid or triangle? See that? Right. You guys see that, right? Like this rectangle equal to the area of this trapezoid. This little tiny rectangle on here, same area as this little tiny triangle, and so on. Right? Okay, so I can still do that trick, except now this distance, guys, this rectangle I just hatched in right here, is that more than or less than 50 meters? It's got to be less, right? I could probably do a calculation, but it's definitely less than 50 meters, right? And this one is even less than that, isn't it? And this one is a little bit, right? But it's a tiny bit, right? It's just a few meters or something, right? So notice that the entire time this car is going forward, it's still accumulating positive distance, right? But it's just at a lesser and lesser rate. So at time 4 seconds, it's not going to be like up here. It's going to be a little more like maybe like right here. And then 5 seconds, and then 6 seconds. What it's going to do, this is going to kind of curve down sort of like this. If I do this right, it's probably close I can get it. Right. Guys, what shape is that right there? Parabola. Right? And what point on the parabola is this right here where it comes to a full stop? Vertex. Yeah. There's the vertex of an upside down parabola right there. Is that like that? Is that right? Let's go back to this method I was doing with the rectangles, right? Because I have 3 time intervals where it's slow to a stop. You guys see 3, right? Well, what if I didn't do 3 time intervals? What if instead of 3, what if I do 300? Just like have a bunch of little tiny trapezoids all next to each other, all like thin as a toothpick. You guys see how that? Right? That's like 300. Right? Right. Oh, the more and more granular, the more tiny I make these rectangles, isn't it just going to better approximate this triangle to start with, right? Which gets me to this idea of, what if I have some crazy velocity versus time curve? Let's do this. Let's do this. Right? Let's say we go out to the highway, right? And I'm gonna do this. I'm gonna do gas, brake, gas, brake, gas, brake. I'm freaking out everybody around me. The cops pulling me over. Get off the road. All right, gas, brake, gas, brake, gas, brake. Could look like that, couldn't it? Right? Guys, what does, so some crazy Dr. Seuss looking curve. What does this area right there represent? How, what? Distance. Yeah. How far have I driven? Yeah. How much road am I causing my reign of terror? Is that? You're right. All you have to do, you can split this into, again, like 300 little tiny rectangles. Do base times height for every one. So like 1 foot there and 1.1 feet there and 0.9 feet there. Just add them all up. All right, there you go. And to close this whole thing off, because this entire thing we've been talking about the last few minutes, does anybody know what branch of math this is that I've been taking you guys through? Huh? Who said calculus? Calculus, yeah. Guys, this is integral calculus. If you're in a calculus class, you're taking calculus someday, probably closer to the end of the class, they'll do exactly what I did. Right? It's called integral calculus. All right, so back to here. I think you guys then know the answer to these graphs up here. All right, you guys figure it out? You guys figure out this is gonna, so here's the constant velocity bit. It accumulates displacement at a constant rate. And then you take your hand off and it slows down. So you draw a parabola. So it's still moving forward, still spinning counterclockwise, or mine was, but a slower and slower rate until it comes to a stop. And then if you multiply by the radial size, like the radial distance of my outside Roosevelt, something like that, you can say, like, how far has he been wheeling around that circular racetrack? And okay, it'd be at a constant rate for a while, and then slows down and still moving forward, but slower and slower and slower until it comes to a stop. So a straight line followed by an upside down parabola, ending at the vertex. All right. All right, you guys good? All good? All right. Right. Now hold on to this paper, because on the back side is a different lab. This is centripetal force lab. You guys, it's centripetal force lab. There's a table, there's a bunch of graphs. It's gonna take us a couple of days to do this next part. All right, so let me go back to my posters and fill you guys in and bring you guys up to speed. Right. Right. So I actually got some middle posters. It's gonna bridge us over. Right. So we just finished this turntable kinematic lab. Just finished that one, right? And so moving on. Right. Oh, whoops. Oh, here we go. Actually, you guys do have a poster for that. Almost forgot this one. Right? Yeah. No, this is just the second half of your story. Here's slow to a stop. Here's theta, omega, and alpha, all versus t. Hey, look at that. Is that all similar to what you just drew? Right, just the second half of your story. You guys got that? Okay. Notice I have this turntable. Here's theta is angular displacement. Omega is angular velocity. I have this thing turning counterclockwise. But look at that. The angular acceleration is going clockwise. Oh, because it's slowing down. But these two are opposed. They'll slow down. Okay. All right. Here's this one's trivia, but I've been doing this one today. So let's hit this one here. So how can you play music back in the 20th century? Well, if you go back to the 1960s, you guys have these long play records. So you put this needle in this groove. It's a physical groove. So as this thing rotates, this groove spirals in towards the center, and there's this needle that hits these ridges, these bumps, and vibrates up and down. Connect that to a speaker, amplify it. Because sound, is sound just vibration? Sound is just vibration. You can hear my voice right now because there's pressure waves in the air between my voice and your ears. That's how you're hearing me. Okay? So that's how this works. It's an analog system. Now, this record would rotate at a constant angular velocity. But there's an interesting consequence then for the linear speed between the needle and the surface. Guys, if this is rotating, for example, 33 1/3 revolutions per minute, when the needle's on the outside, so you're playing the first track, needle's on the outside, doesn't have to complete a huge circumference in one revolution versus when you play the record, let's say you get to the last track, right? And now the needle's really close to the inside. Isn't that a much smaller circumference? It doesn't move as far. So this needle effectively, the linear speed between the needle and the surface slows down because the record is rotating at a constant rate, right? Now, fast forward a few decades. Let's go to, let's call it the 1990s. Get the digital version with the CD, the compact disc. Now, instead of a needle, you have a laser, right? It also goes from inside to outside. That's a little trivial difference, right? But guys, isn't this all just bits, like zeros and ones, right? So if it's a bunch of zeros and ones, what engineers figured out is that there's only so many zeros and ones you can fit on the inside ring on the first track. But by the time you get to the last second of the last track, guys, there's a huge circumference out here. You can fit so many zeros and ones. You can fit a lot more zeros and ones out here. Okay? So between the laser and the CD, think of that being kind of like a constant linear speed, right? But the consequence is that you actually have to slow down the CD over the course of it playing in terms of angular speed. So it starts out spinning really fast, but then by the time you get to the last track, it's actually spinning slower. Interesting. Right. Other trivia posters. Focal pendulum. I think we did this one last week. You guys saw this one last week. Same thing, Coriolis effect. I had to show you guys this one because the hurricane was coming. This explains hurricanes. And so we talked about those. You can catch that in the last video if you want to see a review on that. All right. We're heading into centripetal force labs. So I need to throw two terms on the board and distinguish these. Centripetal, centrifugal. So how are those different? What do they mean? What am I going to talk about? So centripetal means a center seeking force as perceived from an inertial frame of reference. That's to say a non-accelerating frame of reference. That's like, here, oh, here's your turntable. Here's the Roosevelt I had on my turntable. You see that? My Roosevelt on my turntable? Now, there's Newton's first law of motion says that there's something at rest and wants to stay at rest, but guys, anything in motion wants to move how? Like straight line, constant velocity, right? Does anything ever want to follow a curved path according to Newton? No, right? And if it is following a curved path, that's because there's some force that's causing it to do that. So I would draw this free body diagram this way: weight, normal force, and a friction force. And guys, look at that friction force. Is that friction force pulling the coin in towards the center, or is it throwing it towards the outside? Which way is the friction force acting? Yeah, it's pushing it towards the center, right? Now, if the friction force suddenly disappeared, the coin would fly off tangent to its motion. Maybe you have to think like in 3 dimensions, like flying outside the paper, right? It's like towards us, right? But you leave the friction there. Yeah, the friction force is preventing the coin from flying off in a straight line path. It's pulling it, it's forcing it to stay on the curved path, force it towards the center. Okay? That's from our point of view. Our point of view is this inertial frame of reference. You're sitting in your seat as an outside observer watching the turntable rotate. And that's exactly the free body diagram you set up. Right? Now, centrifugal is what happens if you're in the rotating frame of reference. Okay? Guys, if you're sitting on a merry-go-round and you're spinning, which way does it feel like you're being thrown? Towards the inside or the outside? Does it feel like you're being thrown away? Being thrown away? Right? Now, really what's happening is that you're always trying to move in a straight line, and maybe the bars on the merry-go-round are forcing you in, is really what's going on. Right? But if you blindfold yourself, it feels like you're being thrown away, which is instantaneously sort of true, right? But it's really just law of inertia, right? So you would say, oh, it feels like I'm being thrown towards the outside, a center fleeing force. I'll call it centrifugal. But again, you can only perceive that from a rotating frame of reference. Like you have to be on the merry-go-round, or maybe on your turntable, you have to be a ladybug that like lands on your turntable to experience it, right? Oh, guys, look at this term. I put in quotation marks. Fictitious. Guys, if you read a fiction book, is that true or not true? Fiction means not true, right? Fiction is not true, right? This is a fictitious force. It does not actually exist. There is no force that's ever actually pushing anything towards the outside. But if you're in the rotating frame of reference, you think there is, okay? But I'm going to use the word centripetal. I might not ever say this again. I might not ever say centrifugal. I'll just say centripetal, okay? I'm going to do this one. All right. So brings us to this lab finally. This lab. Tell you guys a little bit about this today, so you can go home, sleep on this tonight, and then tomorrow we're gathering this data, so know what to look for. So here's the setup. I got a PVC pipe, a string, and a couple of canisters, and I've got some equations here that I'm going to cover up because I want you guys to figure out these equations. Here it is. Here's my PVC pipe, my string, my Play-Doh canisters. The Play-Doh canisters, they're safe, so if anybody, I'm about to get the swing into motion. If you get bonked in the head by this little Play-Doh canisters, it's not going to hurt you. Right? Also, the fact that these have lids, hey, you know what I can do is I can take these masses, I can put them inside, and I can seal it shut. You see that? Right? Now, can you guys hear that? Right. This one's really heavy. This one's empty. It's only 6 grams. 6 grams is empty. This one, it's like, well, I put a 50-gram slug in this guy. So, guys, what's 50 plus 6? 56. Right. So I got 6 grams versus 56 grams. Right. I'm going to spin this around in a circle. It's going to look like this. The string is going to hold these 2 canisters together right through the pipe. Right. It's going to be held up. Now, this one, when I do this in front of you guys, if you're watching the video, use your imagination. It's just going to be this in the classroom. You'll be able to see this. This bottom one is going to be in true static equilibrium. It's not going to be moving up or down. So you got to weight down and tension up. It's held in place. But the one swinging around, that's on a curved path. Is that true equilibrium? No. I might call it dynamic equilibrium because this radial size should stay the same, but it's not true static equilibrium. There's a net force. Hey, look at this tension right here. That tension. All right, so here we go. Do this in class. Is this so now? All right. Now I'm keeping a certain speed to keep this all. And again, top guy's dynamic equilibrium, which is not true equilibrium. But the bottom guy is a true static equilibrium. Look, he's not even moving. This bottom guy is. Okay. Now, what if I spin it slower? What's going to happen to the radial size? Yeah, it's getting smaller, shrinking. What if I spin it faster? What's going to happen to the radial size? Ooh, look, it's growing bigger, bigger, bigger. Huh. Right. So now I'm already starting to play around with the variables in my head. Let's keep track of how many variables are on the board here. Okay. I guess speed was a variable and radius was a variable, right? Because the faster I spin it, the more the radius opens up. You guys just saw that. What about these canisters? What if I change out the swinging mass or the hanging weight? Could that also maybe change how fast I have to spin it to maintain some radial size? Right? If you keep a track, that's 4 potential variables: the swinging mass, the hanging weight, the radial size, and the equilibrium radius, and the tangential speed to maintain that. Okay? So I'm going to split you guys into 3 different teams tomorrow. 3 different teams. So one team is going to each team is going to control 2 of those 4 variables, and everybody's going to relate everything to speed. Okay? So maybe, for example, you might be in a team that keeps the canisters the same throughout the day, but maybe you start with a small radius, test that out, then medium radius, and then later on a large radius. Say, what corresponding speeds do you need to maintain that? One more thing here. How do you think you get the speed? Do you think you can calculate speeds by doing how far around divided by how much time does that take? And what if you do like 10 revolutions and time that and then divide by 10? Doesn't your error of using the stopwatch also get divided by 10? Right? So plant those ideas there. So tomorrow you're going to be in one of those 3 teams, and yeah, we'll get some data. See you guys then. You guys have a good night.